Hello, this is Dr. Vev. In the previous video, we talked about differentiating under the integral sign as a general technique of evaluating integrals that are normally impossible to do by traditional means of calculus. Here's another example. I have to evaluate the integral shown here. The regular techniques of calculus utterly fail for an integral like this. How to proceed using our new technique? Well, the first thing is you've got to be pretty bold and make up an integral for which this is a special case. Let me define an integral I of alpha comma beta to be the integral from 0 to pi over 2 of the natural log. I'll replace 4 by alpha and 9 by beta. That's the first step in the abstraction. Alpha and beta I'll take to be real numbers. So in doing this integral, I'll be actually evaluating an entire class of integrals where alpha and beta can be any real numbers, not even integers. So that's the big payoff. Now let's try to see what I would get. Either alpha or beta can be picked. I'll just pick alpha. If I differentiate with respect to alpha, does this integral become anything simpler? So that's going to be the integral from 0 to pi over 2. By using the technique of differentiating under the integral sign, I go inside the integral sign and differentiate with respect to alpha. The natural log of something, when differentiated, becomes 1 over something. So I'll get 1 divided by all of this argument. So alpha cosine squared theta plus beta sine squared theta, and then because I'm differentiating with respect to alpha, I'll have to go inside and use the chain rule. So when I go inside and differentiate with respect to alpha, I will pick up cosine squared theta in the numerator. So that's the answer. If I had chosen to differentiate with respect to beta, the only difference would have been I'll get sine squared theta in the numerator. Everything else would be the exact same thing. So you can either do alpha or beta. There's no rule there. This can actually be very simply evaluated. If I divide both sides by cosine squared theta, I'm going to get integral 0 to pi over 2 d theta divided by alpha plus cosine squared over cosine squared is 1 and sine squared over cosine squared is tan squared. So alpha plus beta tan squared theta. Now we can use the u substitution. Let us say that u is equal to tan theta. Let's see what that gives us. So the u substitution can be tried. Then secant squared theta d theta equals du. Unfortunately, I don't have secant squared. I have just d theta. So I have to solve for d theta. So d theta is du divided by secant squared theta. Secant squared theta can be written as 1 plus tan squared theta, and tan squared theta is just u squared. Now what about the limits? The limits when theta equals 0, that is the same as saying u equals 0. When theta equals pi over 2, u is infinity. So the limits are from u equals 0 to infinity. So I have actually simplified this integral a little bit. Let me write the simplified integral. It's an integral from 0 to infinity of du. D theta is du over 1 plus u squared. And when I put u here, I'll get alpha plus beta u squared. Now, that's still pretty complicated, but nothing as frightening as what we had initially. So we still have to do some work. This type of integral can be solved by an elementary calculus technique known as the partial fraction decomposition. So what I'm going to do here is spend a few minutes doing that. So what I'll write this integral that we want to work with as a sum of two fractions. I'm going to write it as a divided by 1 plus u squared plus b divided by alpha plus beta u squared. Now, the idea behind partial fraction decomposition is to adjust these coefficients a and b so that this must be true. Now, how do you go about doing that? Well, one way to do that is to take the common denominator for the right hand side. Then I end up with the equation 1 equals alpha plus beta u squared times a plus 1 plus u squared times b. Now this equation is interesting because the left hand side is just 1 and the right hand side has got a bunch of stuff involving u. So obviously all the coefficients of u squared and u to the power 4 must be 0, and the coefficients that are constants must equal 1. That in fact pegs down really what a and b should be. So let's try this out by writing it one more step. 1 equals, so I'll get alpha times a plus beta plus beta plus b, excuse me. Then I have beta times a, that's all multiplying 1. Then I have multiplying u squared, beta times a plus b. And there's no u to the power 4 term, I misspoke earlier. So these are the two terms that you have. Alright, now what to do? The coefficient of 1 and alpha a plus b must be equal, because I can write one more step just to make this very clear. 1 times u to the power 0 plus 0 times u squared must be equal to alpha a plus b times u to the 0 plus beta a plus b u squared. So in this, if I write it in this fashion, it's very clear what's going on. You have to set the coefficients equal. So alpha a plus b equals 1, beta a plus b equals 0. Let's solve that system. One way to solve the system is to subtract, getting rid of b. So I'll get alpha minus beta times a equals 1. Well, that immediately tells me what a is. A is 1 over alpha minus beta. Okay, now once I have a, I can find out what b must be. I'll just substitute it in one of these equations. The easier equation to use is the second one because it's got a 0 on the right hand side. So I'll write b equals negative beta times a. Well, a is already known, so that's going to be negative beta divided by alpha minus beta. So we have accomplished our mission. So what I will now do is evaluate this integral. So going back, I'm going to write del I by del alpha is equal to, that thing is now equal to the integral 0 to infinity 1 over alpha minus beta times 1 over 1 plus u squared du plus minus, because b has got a minus, so that's minus beta over alpha minus beta times du divided by alpha plus beta u squared. So two very simple integrals because these are just arctangents. So I get 1 over alpha minus beta. The integral of du by 1 plus u squared is a standard integral. It's arctangent of u between the limit 0 and infinity. And here I have beta divided by alpha minus beta. Now this is also an arctangent substitution. However, the only difference between the previous integral and this integral is the presence of alpha and beta. Well, alpha does not matter, but what beta does is it produces a constant up front. So the proper substitution to use here would be substitution that u equals the square root of alpha over beta times tan theta. So if I use, sorry, I should have called it some other value like phi, because theta is already used. So if I use this one instead, then you'll notice that, let me just spend a couple seconds with this integral. So the du here will be alpha over beta secant squared phi d phi divided by, in the denominator, I'm going to get, when I substitute for u squared, I'm going to get alpha over beta. That beta will cancel this beta, and I'll just get an overall alpha in the denominator, and then I get 1 plus tan squared phi. Well, 1 plus tan squared phi is the same as secant squared phi, so that can cancel out. And the alpha in the denominator will dominate over the square root of alpha in the numerator, so I'll get 1 over root alpha beta at the end of the day, and then I'll just get phi. Okay, but phi is precisely the arctangent of beta over, let's see, if I solve for just tan phi, I'm going to get square root of beta over alpha times u. So when I solve for phi, that'll be the arctangent of that whole thing. So that's the answer. Okay, with that done, we'll put that here. So that's going to be 1 over root alpha beta times arctangent of square root of beta over alpha times u. Also between 0 and infinity. Fortunately for us, the lower limit doesn't contribute. The upper limit is just pi over 2 for both cases. So I'm going to end up getting just the upper limit. So that's 1 over alpha minus beta. It'll be common for both factors, so I'll just write that first, times pi over 2, 1 minus, and here I have beta over root alpha beta. Well, that's interesting because one of the betas cancels out and I get root over there. So that's going to be pi over 2 divided by alpha minus beta times root alpha minus root beta. There's one more thing you can do with this to make it look a little cuter. Alpha minus beta can be thought of as root alpha minus root beta, root alpha squared. So I can write the, let me just writing it is easier than explaining it. So I'm going to write alpha minus beta as root alpha plus root beta times root alpha minus root beta times root alpha minus root beta. So finally, I have my answer. It's pi over 2 divided by root alpha, actually I forgot one factor of root alpha, because when I get this thing here, and here I have a root alpha in the denominator. So that's root alpha, and now I have this answer, root alpha times root alpha plus root beta. All right, so I've evaluated my answer. Now, we have not finished the problem, far from it. We have only evaluated the derivative with respect to the variable. So let me recap what we have done. Just take a couple more minutes. So del I by del alpha has been shown now to be pi over 2 divided by root alpha times root alpha plus root beta. Now I'm going to make another u substitution, or rather I'll call it a v substitution this time because u has already been used. So I'm going to use square root of alpha plus square root of beta equals some quantity v. Then 1 over 2 root alpha d alpha, because I'm going to try to integrate this again, is going to be dv. So when I try to integrate this, I'm going to get I equals pi over 2 the integral of d alpha divided by root alpha times root alpha plus root beta. All right, and I'll use the v substitution and I'll end up getting this is equal to that the root alpha is already there, okay, and the 2 is already there also. So in a sense it's already made for each other, and I end up getting pi times integral dv over v. You see, because dv has got d alpha over 2 root alpha, which is already here, and then v is just that factor root alpha plus root beta. Well, that's just a natural log, so it's pi times the natural log of v. But be careful, we have to add a plus c because this is an indefinite integral. So the next challenge is to determine this constant of integration, natural log root alpha plus root beta plus c. How to determine plus c? Well, if you go back to the original integral, and this is all equal to I of alpha comma beta, if you go back to the original integral, alpha and beta appear in front of cosine squared and sine squared. Well, we know one special value, and that is cosine squared plus sine squared equals 1. So let's choose alpha equals 1 and beta equals 1. Okay, that will be a great way to fix our initial conditions. So what is I of 1, 1? I of 1, 1 is the integral from 0 to pi over 2, the natural log of cosine squared plus sine squared. That's everybody's favorite quantity. It's equal to 1, and natural log of 1 is 0. The integral of 0 is 0, so I get that equal to 0. But all that is equal to also this. So this is going to be pi times the natural log of alpha is 1 and beta is 1, so that's root 1 plus root 1, which is 2, plus c. In other words, I've established that c equals negative pi ln 2. Highly non-trivial constant of integration. You could not have set it equal to 0 rashly. The last step is to figure out what I of alpha beta is, our initial alpha beta values. So that's going to be pi times, it's going to be pi times natural log of root alpha plus root beta minus pi times natural log of 2 for the constant c. So I can write this as pi times natural log of root alpha plus root beta divided by 2 using the property of natural logarithms. Now finally we can get our answer because I of alpha is 4 and beta is 9. What is that? It's going to be pi times natural log of root 4, which is 2, plus root 9, which is 3. So our initial integral has been evaluated. Quite amazing.